Hey, good morning. Good morning. Welcome to week 10. Week 10, week 9. Week 9, 10, 11.
I think
2
it's
more
week
weeks of
9.
classes. It's week 9, yeah. And so you only have 2 more weeks of classes and then a final week 12. Obviously, we can have a class in week 12. We can have a class. I'm happy to give you a class in week 12. No new material, but if we have some interesting and exciting projects we're working on, I mean, we can still get together on, in week 12. Okay, so today's plan is to look at recursion. And I was thinking, well, if we have time, we'll also introduce pointers. Okay, you got to encounter pointers next week anyway, so might as well start introducing pointers. Maybe what we'll do, yeah, I think what we can do is play with recursion, and that will set the stage for learning about stacks. Your first formal ADT that you'll implement, and we will implement stacks using pointers, and heaps, heap memory, real heap memory, which is different from what you'll have to do in quest number 8. And so that'll give us an opportunity to work with stacks, understand stacks, and also, know the part they play in recursion. Okay, all right. So that's what we'll do today. Why don't we start in about 5 minutes when people join us? I'm not sure there's a whole lot to code today. Well, there might be some to. Yeah, I don't know. We'll see how it goes. Okay. Next class, next week there'll be more. I think pointers and pointer wrangling. There's a lot more to work with pointers next week. Doesn't matter, even if you code this week, you can come back and code next week. That's okay. All right. So why don't you guys just talk? Yeah, for 4 minutes. Okay. Well, we'll start at 8:10. You guys chat amongst yourself for about 4 minutes. And Hannah, you're ready to code today, right?
Yep.
And do you have a Mac or you have a PC? You said you have a PC, yes? You have a PC. Okay, yeah, great. So so we can have a little Hannah code today, and we will work with stacks and pointers. Okay, five minutes. Just go ahead, talk. Nobody produced any blockbuster movies after after Totoro, but doesn't matter. Keep working on it. Something interesting might come up. And then plus there are lots of concepts in what we did before that will impact what you're going to be learning now. So it's very important to not just know how it's done, but practice that thing repeatedly, what we did last class repeatedly, so that hey, that's an ampersand, so it's passed by reference. Hey, that's constants, you can't change it. Oh, it's static, right? So there's only one copy of the variable or the method. All those things that just need to be internalized. You can't just look it up saying, hey, I need to do this thing in C++. How do I do it? Let me see. Oh, there's something called static. I think I learned about that a long time ago. So I can bring that back. No, that never works. You need to know. But when you look at the problem, you already say, oh, right, okay, I can solve this problem. I can put a static there, a constant reference here. Okay, there's a solution. Okay, so like that. That's the way to solve bigger problems. Otherwise, you'll still solve some smaller problems. But solving smaller problems stops getting interesting after a while. Now it's interesting, okay? As you're learning to program, so solving small problems is interesting and it's fun because you see unexpected things happen. But after a while, it gets boring to solve small problems, and you want to, you're looking for bigger, interesting problems to solve. At that time, it'll help if you have all of this internalized, not just know how to do, internalized. That's a very big difference, okay? And I don't know why they don't emphasize this in computer science classes. They have to emphasize it. They emphasize this in all of the other, if you go to art, they actually emphasize this. It's not enough to know how to do this. You got to practice and just internalize it. And computer science, I haven't seen any class, any instructor, even online, right? There's lots of courses online too. They don't emphasize that, this is how you do it, but you have to keep doing it repeatedly until you internalize it. And it's just an art. You have to internalize it. That is something that needs to happen. Okay, so all right, okay. So you guys talk, and then we'll start coding in about 5 minutes. Okay.
How's everyone's Tuesday going?
It's going. How about for you?
Going pretty cold.
My school wrapped up their performance of Mamma Mia. I'm working on the crew, so
Dang, that's so cool.
yeah. If you guys, there's gonna be performances in 2 weeks. If you guys would want to check that out.
Oh, you should like drop the link or something. That's awesome. So it's pretty badass being in crew. Like that's like a lot of like work and stuff. Like that's awesome. Everyone's projects or questing going okay? Same. Same vibes.
Is everyone here like gonna continue on to like the 2B course?
Yay. So you might see some familiar faces next quarter, maybe? Sweet. Yeah, I feel like I've learned a lot. Especially these last like a couple weeks, just like
All right. Okay. Well, it looks like the conversation's drawing up, and great. Okay. We can. How about today? Yeah, Hannah. When you pick up the screen, are you going to be using online? Well, we can use online GDB initially, and then you can switch to VS Code if necessary later on. This is so strange. Okay, so even into week 9, we're still using online GDB. Last quarter and all, last quarter or even the quarter before, I think we couldn't use online GDB after week 4 maybe, and people had to use Xcode or VS Code. But somehow this time it's just worked out. We just continue to use just the online environment. It's all simple, and we don't have to save code and projects and mess with folders and directories yet. That's cool. Excellent. Excellent. All right. So yeah. So clear off the file and put a comment on the top at the top saying, you know, class code for what's today's date? Yeah, March 7. Well, and you can put a comment under that saying today we'll play with recursion and yeah, get an idea for its yeah, advantages and disadvantages. Yeah, I think. Yeah, right. So yeah. Okay, let's do the, yeah, thank you, Hannah. Yeah, so. Okay, great. In fact, you know, it is harmless. What you've done is harmless, and I've seen programmers do it too. But my preference may not be your preference is to not have parentheses around the 0 on return. The reason being, return is a keyword, not a function call. And then the 0 makes it look like a function call. And then some, some programmers might get confused. I don't know. Once you have a little bit of experience, it's not a function call, but still. All right. Okay. Great. So I'm thinking, should we just do a global recursive function or a class with a recursive method? Why don't we do a class with a recursive method? Okay. We'll do a class with a recursive method. I think that's better. Okay. All right. So above main, let's go. And we can create a class, blank line above that. Yeah. And then a blank line below that too, so that it's separated out from main. Yeah, okay. So you can say a class, and then you can say recursive functions.class or recursive methods.class, recursive methods. Just call it recursive. Yeah, recursive methods. Okay. All right. Now, yeah, curly brace, and then semicolon at the end of the last curly brace. Okay. So here's what we'll do. Recursive method is such a big word. And every time we call a method, we got to type in that entire thing. Scratch the class. Okay. Yeah. Unless you guys really want to. I'm going to assume that you guys are comfortable with classes, basic classes and stuff like that. We don't have to do it in classes because with classes, we just do recursion, because recursion on its own, you can just take it and put it in classes and it'll work just as well, exactly the same way. So yeah, Hannah, if it's okay with you, let's not do a class. Okay, we'll just do a recursive method. All right. So before we do that, just want to do a very brief introduction. So a recursive method is basically a function or a method that ends up calling itself. Okay, so in the method it's going to call itself. Now, when you do that, what is the danger? What is the danger of a method that calls itself?
Like that it never stops. Like we don't have it.
Right. Okay. So it's like an infinite loop, right? It's like an infinite loop, meaning that it calls itself and keeps calling itself. It never ends. Yes. However, that is not true, right? If you have an infinite loop, you'll see that the program is just running away, right? It's just running and running and running for hundreds and thousands of years. It'll just keep running. But a recursive method, if it is unchecked, like a loop without an end, will not go like that. Okay. A recursive method will go to a certain depth and it'll die. I'll say, I don't have any, let's test it out. Okay, so let's say void, yeah, type void. Hey, there's a lag. I don't see, also the real estate on the screen is not taken up fully. There's only a small band in the middle and there's a, two black
Sorry
bands.
about that. I don't know. I think my computer.
Yeah.
Right, let me share again. Can you guys see it now?
Yeah, I can see your screen. There, that's much better. And you can dismiss the blue panel. Dismiss the blue panel.
Oh, this guy.
Yeah, yeah, I think that's much better. All right. So let's type a void, and then we'll say yeah, we'll say bad recursive method. Okay, bad recursive. Call it bad recursive method. Bad recursion. Just call it bad recursion. Bad recursion. Okay, and then yeah, right, a curly brace and then curly brace and enter. Right here, we're going to do something. We'll just say cout, left shift. And in here, let's create a static variable. Again, this is a feature that is when you look at the method and try to understand it, you'll see, hey, that's what static variables are. Okay, because it's different from global, local variables. So let's put a static variable inside this method. Go to the end of line 6 and hit enter. Yeah, and say static, int n equals 0. Okay, a semicolon, enter. Yeah, I put an enter after that. All right, now you say on the cout line, you say open quote n equals n equals n space equals and then close quote and then n left shift n. No, left shift n. Left shift operator, 2 less than signs. No, not backslash n. Left shift and left shift is the 2 less than signs. 2 less than signs. And then left shift again, and then open quote, full stop, a period, and then a period and 2 spaces. Now recursing one level deeper. Now recursing one level deeper. Say type now recursing one level deeper. Yeah, okay. Now you can do your endl, close it and endl. And endl, yeah.
Wait, sorry, how do I do that again? I haven't coded in so a while.
Yeah, okay. ENDL. Yeah, and L. Semicolon. No, and L and semicolon. Yeah, enter. Now here, you're going to call this method itself, right? So you're going to say bad recursion, call bad recursion. Open, and then put a comment on that line. You put a space before the comment starts so that it's a separate token and all, right? Yeah, right. Now say this is unchecked recursion, right? Say unchecked recursion. This is unchecked recursion. Yeah. Okay, great. Now let's go to main and call it, right? Let's go to main and call it. Now, when you run this method, what is going to happen? So before, don't run it. So and this, you just make it a habit. All of your programming courses, whether with me or other people, when you code, live code or anything, don't hit run at all. Even when you're, especially when you're a professional and programming with other people, right? You write some code with other people. You don't test it out by hitting run and saying, oh, well, let's see what happens. You always run it in your head first. Okay, so what is going to happen now? Take a guess. Okay, take a guess. What is it going to output? Or if it is going to output anything at all.
Is it going to output n equals 0?
Okay, and then what? And what will happen after that?
N equals 0. Now recursing one level deeper.
Yeah. Actually, you know what? We forgot something. On line 9, after the left shift n, on line 9, when you have inside left, yeah, there you go. Turn that n into n plus plus. Okay, now there's lots of features. Even though this is just a simple program, it uses a lot of features that you have learned before. So it's really imperative that you go through this code and run it in your head and see what's going on. All right, so Sabrina started off with the right answer. The first part, the initial part of the right answer. Okay, so the first thing it's going to say is n equals 0. Yeah. So what is going to happen after that? What will it do after printing n equals 0?
Is it going to increase by 1? It's going to increase by 1.
Yes, it will increase by 1, and then what will the program do? What will we see happen? What are we going to see happen?
Are we gonna keep seeing the message pop out with like the new numbers?
Yeah. Okay. So in fact, so it'll say n equals 0 on the next line. It'll say n equals 1 on the next line. It's going to say n equals 2 and so on and so forth, because it's just calling itself repeatedly. However, n is a static variable. Yes, it's a static variable. Therefore, when you change the value of n, the next time the function is entered, it retains the old value. That is the power of static variables. Okay, this is different from local variables. Local variables are also called automatic variables. Okay, and later on when we talk about stacks, you'll know exactly what the hell is going on, because the static variables are not on the program stack. They're stored elsewhere. Okay, so which means that this n, when you change, if you change the value of n here, it's changed for good, right? Until the program dies, the value of n is changed, or until the value of n is changed explicitly again, it's different. So it'll say n equals 0, next it'll say n equals 1, n equals 2, and so on and so forth, right? So is it going to do that forever, for hundreds of thousands of years? Yeah, well, Erica's shaking her head. You know, that's good enough of an answer, right? Because you can see that. Well, it's well, hundreds of thousands. Well, I said hundreds of thousands years. What is going to happen? Well, we'll find out. We'll find out what the stack depth is on this computer. Okay. Well, if you run it now, you'll see what is going to happen. And chances are online GDB is using, I think it's just using Linux or something. It'll just die, right? It'll die at some point. And well, well, you know, that's how deep the stack is. Wow, this is cool, right? So and so n is increasing, which means, look at that. This is really cool and important, right? Now this, when you say n, when it says n equals 20,000, okay, it has made 20,000 calls to that function, and each of those calls is inside of each other. So it's actually deep, right? It's gone into the function and called it from inside. It's called it from inside. It's called it from, basically it's digging deeper and deeper. It's gone that deep in, right? Now n is an integer, isn't it? It's an integer, and already we know that it is not, just by looking at the output, we know that n is not a 2-byte integer on this architecture, right? On this machine that they're hosting it on in the cloud somewhere. It is not a 2-byte integer, right? N is actually a 4-byte integer. I think it's 4-byte, could be 8 bytes, I don't know, right? It's 4-byte integer. It's a long integer by default. Now, how do I know? How do I know that n is not a 2-byte integer on this computer? A remote computer somewhere in the cloud, I haven't seen it. It may even be a virtual machine, but I can tell right now by just looking at the output that n is not a 2-byte integer. It's a 4-byte integer. How can I tell that? Take a guess, okay? All of this ties in. All of this ties in. Starting, in fact, you know, the question I just asked goes all the way back to week number 1 when we talk about data representation. Yes, and that's how everything is related. And yeah. So take a guess. Why? How do we know? How do I know that that integers on this machine, this architecture, they're not 2-byte integers, they're 4-byte integers, bigger integers? How do I know that? How can I make that call?
Is it because of how big n can get?
Yes, and what is if it was an integer, how big could it get?
Wait, I know this. Is it like
Isn't it 7 numbers long? Because the last one's the
yeah.
positive or negative, or like the one.
Yeah. No. Yeah, it is signed. It is signed. Okay, it is signed. So it is 7 bits per byte. 7 bits per byte.
But if it's 7 bits per byte, has it reached? Because it's still at 6, right? Do you just kind of assume that it's can go past that?
No. So if it's 7 bytes for, you know, for storing an integer in 1 byte, if you have a 2-byte integer, if I have a 2-byte integer, this is not 2 bytes. Okay, this is my conjecture is that machine which you're running it on in the cloud is actually 4-byte integer. If it was a 2-byte integer, then that means if it was signed, because it's signed, we're not saying unsigned int. Okay, it's signed. It'll use 15 bits for the value and 1 bit for the sign. Does that make sense? There's 15 bits for the value and 1 bit for the sign. Okay, so how can I tell that this is using 2 bytes for, 4 bytes and not 2 bytes? And Namrata had the answer. So it, because of the value of n is so big now. So what is the maximum value of n you would have expected to see before something weird happened? Something weird happened, right? What is the maximum value? Basically 2 to 15, right? Okay.
I don't know how to say this number, but 2147483648.
No, actually, yeah. Good guess. Was that Sabrina?
Yeah.
Right, good guess. Right, so that number that you said 21, I don't know the full number, but I know it starts with 21. Okay, that number is actually the biggest possible number you can have with 4 bytes, not 2 bytes. Yeah, okay, so if our integer was 4 bytes, in fact, you will see what happens. You know, you'll see Sabrina's number come up here at some point. You know, when it goes all the way up to 21 billion, you'll see that number come up. However, it is not. So 15 bits is 2 to the 15. Yes or no? 2 to the 15, isn't it? Because 1 bit is gone for the sign. The leftmost bit is a sign bit, and then you have 15 bits left. In 2 bytes is 16 bits, 1 bit gone, 15 bits left. Now 2 to the 15, we got to calculate 2 to the 15. How can we calculate 2 to the 15? It's really hard, isn't it? So, but however, 2 to the 15 is done, and it has easy ways to do this. Okay, so 2 to the 15, and this is, I think this is called it's called right. So right, 2 to the 15 is 2 to the 10 times 2 to the 5 is 2 to the 15. Yes or no? And what is 2 to the 10? 2 to the 10 is quite easy for most of us to know, right? So 2 to the 10 is basically 1024, because 2 to the 10 is, how do I know 2 to the 10 is 1024? Yeah, maybe because I've done it many times. It's a useful number to keep in your head. Okay, 2 to the 10 is 1024, 1024. Because, you know, 32 times 32, 2 to the 5 times 2 to the 5 is 2 to the 10. 32 times 32 is, you know, around 10,000, you know, around 1,000, isn't it? 33 times 33 is close to 1,000. Yeah. So 32 points, right? So 2 to the 10 is going to be 1024 times 2 to the 5. So 1024 times 32. So far, are we good? So 2 to the 15 is nothing but 32 times 1,000, approximating here, right? 32 times 1,000 is 32,000. The actual value really is 32,000. I don't know. I think it's about 32,656, and we can find out. So let's kill this program, hit Control C. We have very deep stack on this machine, okay? Hit Control C. Now change that static int to static short int, short integer, short. Now there is a short comes all the way back from C, right? So when people said, you know, oh, the default integer is a long integer with 4 bytes, they said, no, sometimes I don't want to waste 4 bytes because my numbers are always going to be less than 32K. So they said, give me a special data type that is only 2 bytes. And this does not exist in other languages. Okay, I don't know. I don't think that Java or Python has something, has even the concept of a short integer, an integer that only uses 2 bytes to store, right? I don't know, right? In C++, you can say, I want an integer that only has 2 bytes to store the value. In fact, you can even have an integer that only uses 1 byte, and meaning that you can use a character, which is 1 byte, to store an integer value, because a character is just an ASCII value of the character, isn't it? So you can take a character and say, it's not a character, it's actually an unsigned character. I'm going to store values from 0 to 255 in it. That's possible in C++. So a single character can be used to count values. So if you run this now, you'll see the effect that I had in mind. In fact, you know, kill it 1 sec. Can you kill it? I think what's going on is that because it's printing so much, the output is taking long and it's not getting to the end condition soon enough. So now that we know it's just recursing, just get rid of that, you know, text part after. No. We want that, right? Get rid of the text part. Now recursing 1 level deeper and all that stuff, right? We just need the endl after n++. Just put the endl. All right. Now I think if you run it now, it'll just print a series of numbers. It's not going to print junk. Now you'll see, right? After 32,000, you'll see that something strange happened. Okay, just keep watching. Okay, it's coming up. It's coming up. There you go. All right. After 32,000, it just went negative all of a sudden. Right now, going back to data representation, maybe this could be a question, and not fair to have that question in the final, but certainly it could have been a good question in the data representation quiz. Okay. See, now it became negative all of a sudden. Now, what's going to happen after it goes to 0? It rolls back again. Right? It's positive. So it goes positive all the way. Right? When it goes to the biggest possible number, 32,000 something, right? The 32,656. Yeah, 32,656. Okay. And then add 1 more, then all of a sudden, the 32,655, right? Add 1 more, it becomes 32,656, which is really that sign bit has now been turned on because it overflowed into the sign bit and everything else is 0. So after that, it becomes, 0. And then you add one more, you have the sign bit on, and it's 1. So it's negative all of a sudden. Does that make sense? Okay, so it's going on and on and on like that, and it's not ending. And unfortunately, because of the output, it is not crashing, right? Because we're outputting stuff, it's slow, and talking to the console is slow enough that the program is not running fast enough to crash. Okay, but unchecked recursion will crash your program. And now let's do what Hannah did before. Okay, Hannah just commented out line number 9. Okay, commented out line number 9. Now, if you run this now, it'll basically just crash. Well, it'll say program ended, or yeah. All right. Okay. Well, it says program finished with exit code 0. That is wrong. Okay. This is wrong. I don't know what what that message, that is an incorrect message. The program did not finish with exit. Maybe the program finished with exit code 0. Someone should try it out on a standalone machine and see what the exit code is. That program actually crashed. Okay. It crashed with a non-zero exit code, meaning that it kept doing that. At some point, it just ran out of space in the stack, because what's going on is that every time you call that function, it needs to remember what the previous value is, because after that function ends, here's what you can do. Okay, here's what you can do. Let's modify this function now, right? So now we know that it's going to crash. We're going to make some changes. Okay, so now let's put back line number 9. Let's put back line number 9. Right now, one sec. Okay, after that, what you want to do is say if n greater than 10. If n is greater than 10, then you can just say return. You don't even need braces, because it's just one statement. No, just return. Yeah, and get rid of the braces because it's cleaner that way. Okay, now and then separate out the no, we need to do one more thing. Put a blank line before that, before the line 10, before the line 10. Okay, now we want to do one more thing. Let me hang on just a sec. Okay, and then it's going to return otherwise it's going to return from. All right, so after the call on line 14, right, hit enter. Now, triple click on the line 9, triple click on line 9 and put it after the call also, right? And copy that below. No, but we need it there because we're going to make some changes there, right? And put it there. Now change the before the n equals, say after recursion returned, after recursion returned. No, you want to say that inside the quotes. Say after recursion returned, comma, right? And then you want the same thing on the first comment also. You want to say before recursing n equals, comma, right? Now let's run it now. Great. Now increase the size. Oh, hang on a sec. Oh, because n is constant. Hang on. Okay, yeah, I see. You want to get rid of the n plus plus at on the second one. Yeah, run again. Oh, because it's static, it got stuck on line. Yeah, because n is static, it got to 11 and basically stayed there. Even though the recursions returned, it got changed. Well, what I was trying to do, obviously, was it says 10. It prints all these numbers, and then when it's winding out of recursion, it's going to print what it had before. Okay, and we'll come to that later. Now, let me see if I can change this right now. Give me one sec. Okay, I want to think about, or you can also think about how to do this. What I want to do is as it goes in, it's going to change the value. So let's bear with me. Okay, I'm going to make one change. Very simple change. Okay, so here's what we'll do. We're going to parameterize this function. So bad recursion and say int n right there, int n. Yeah. Okay, now get rid of the get rid of that line, next line. Get rid of the line altogether. Okay, now you're going to say before recursing, and get rid of the n plus plus. Oh, wait a sec. Get rid of the n plus plus. Get rid of the n plus plus. Now, when you call bad recursion on line 13, on line 13, say put n plus 1 there, n plus 1. Okay. Now in main, call it with 0. Call it with 0. You want to do n plus plus? Yeah, it doesn't matter. No, n plus plus won't work because n plus plus will basically increment n, but will send the old value of n. Yeah, there you go. Did everybody understand what Hana just did and why it would not have worked with n plus plus, but it will work with plus plus n? Right? It's a very simple, subtle change, but it's important to know why this would work and why that wouldn't work. In fact, you can experiment too. You can experiment. Let's run this, and then we'll see what happens, and then we'll change the n plus plus to plus plus n to n plus plus, and you'll see a different, right? Increase the size of the console, and you can see, right? There you go. So it went from before recursing 0, 1 all the way, and then it went to 11, and then started returning, and then it's printing the value of n it remembered. 11, 10, and so on and forth, right? Now change that thing that, reverse the change that Hana made, and you'll see that it doesn't work, okay? Yeah, make that change. Now it won't work. Yeah? See, because it's always calling n with the same value. Because n is incremented, but the incremented value of n is not going to make any difference because it's going to be discarded because it's just a parameter. It's a local parameter, and it's after it's incremented, it's discarded. But it was called, made the recursive call before incrementing it. So essentially, it's the same as calling it with the same value of n, right? So that's why the plus plus n matters. Okay, now this is an example of how a function can call itself. But at the same time, we have to be mindful that when you call a function, you have to have a basis case or an exit case, right? An exit situation. And in this case, it is easy, right? In this case, it is super duper easy to see where the exit, recursion is. And oh yeah, okay, it's recursing. I got to have an exit, and everything is covered. Okay. Now the reason it's very important to understand recursion deeply is that later on, you'll be writing recursive methods that have many outs, okay? A function that can exit here, return here, return here. You may have many returns. And it's not, so bad programs, bad style also has many returns. I'm not talking about bad style. I'm talking about well-written programs with recursive methods that have multiple exit points. Yeah, meaning that you'll come across situations where that's the cleanest way to write the function is to have multiple exit points. So many returns there. So when you have many returns and the logic is kind of not very straightforward and you have to think about it, it's super duper hard to make sure that you have all the corner cases covered. Meaning that there might be a small case there where it doesn't even, it recurses, but there's no check at all. It keeps on recursing forever. So it's really, really hard to find out if recursive methods have proper exit conditions. That is why it's the same as in mathematical induction. I said before, I mentioned last class, right? Mathematical induction, it has two parts in mathematical induction. One is called the basis case, and the other is called the inductive step. Yes, or right? An inductive step. Now, the inductive step itself is usually really hard. In many cases, the inductive step is in fact the part that requires a lot of genius and thinking. Oh, this is how the logic is in the inductive step in mathematical proofs. However, the inductive step by itself is useless if you don't have a basis case. Yes or no? Yes, and if you've done math induction proofs, if you don't have a basis case, the inductive step is useless because the inductive step says, if this is true, the previous one has to be true. If this is true, the previous one has to be true, and so on and so forth. And you can keep going on like that for infinity. So how do you know that the entire theorem is true? You only know if the entire theorem is true is, if that says, well, you want to know if that is true. That is true because the previous one is true. And that previous one is true. The previous one is true, right? At some point, it's going to hit something called a basis case. I say, well, that one does not require the previous one to be true. It is just true by itself. Yeah, that is true by itself. So that means that, you don't have to recurse any further. At that point, you can return. That is called the basis case in math induction. And so that's exactly what we're mirroring here. the recursive method does have to have an exit condition. Okay, and so now let's try and do some interesting things with recursion. Many things that you can do with iteration, you can do with recursion, and vice versa. Okay, you can transform back and forth. So we're going to do something very simple
Wait,
with recursion. Yeah, go ahead.
Maybe could we do the Fibonacci sequence? Because I remember there was a quest on that.
Yes.
And-
No, actually, you know what? Well, you will absolutely, Hannah. Right. Remind me to do the Fibonacci sequence. We'll do it towards the end because the Fibonacci recursion is a problematic recursion if you're not careful. Right. It's a problematic recursion, and I want to expose what the problem is, and also use it as an It's actually a fantastic example. Okay, so I'll use Fibonacci as an example of what is called dynamic programming. Okay, how many of you have heard the term dynamic programming? Yeah, Namrata, right? So dynamic programming is just a way of using a recursive approach, not necessarily recursively, right? An approach where a problem, when you have to solve a big problem and you chop up the problem into many parts. Yeah, so you chop up and you say, well, you know what, in order to solve a big problem, I can chop it up. Imagine a problem is depicted like a square. Okay, it's a square. You have a problem and that you have to solve, and it's depicted like a square, and you say, well, I can't draw this big square. You have to paint a big square on a football in a football stadium or something, right? And you say, well, I don't have the energy to paint a big square. However, I know how to paint a small square, and it's exactly the same. So I'm going to go to the stadium and divide up the big square into lots and lots of small squares. Okay, now I know how to paint the small squares, right? And all I have to do is simply do the exact same thing again and again, and the big square will also be painted. Yes or no? Is it a valid strategy to paint a big square? Right? So good. Right now it works. It works in this case because the big square, when you chop it up, there's no waste. Okay, the full stadium is tiled by squares, and no squares are overlapping. Right? If the small squares are overlapping, then the paint job is the paint job still efficient? No, it'll still cover the whole field, right? Because even though the squares are overlapping, you're going to paint over every square. Eventually, the whole stadium will be painted white, right? The whole ground will be white there. So it's going to work. However, is this a good way to do it when they're overlapping? No, it's not good, right? Why is it not good? Why is that way of solving a problem not the best way? And again, I want to say this because that exemplifies the difference between an engineering solution to a problem from a average Joe kind of solution. Because an average Joe, many things out there can be solved by anyone, right? Any human can solve anything. It's just a question of how much time and effort they put into it, right? So if you take a really, someone who doesn't do anything at all, know anything at all, and tell them to solve a problem, then maybe they'll solve it in 100 years. Right? Slowly, right? But maybe because they're doing it really, really inefficiently. But if you go to an engineer or someone who's actually studied the problem, knows how to do these things, knows lots of techniques, and say, you know what, I can do this in 100 milliseconds instead. So that's the difference. And that's why, painting this field, an average painter could do it with overlaps. That means that they'll waste a lot of paint. There's too much work done, moving hands over the overlapping areas and all. So it's lots of wastage. So when you have overlaps in a big solution that's been chopped up into small solutions and the pieces are overlapping, there's wastage. Yes? Because the same thing will be solved more than once, which is what we're going to see this. We're going to see this firsthand when we do Fibonacci later on. So this dynamic programming is nothing, right? But just a formalization of the approach, saying if you have a big problem, which you have overlapping subproblems, okay? Overlapping subproblems, and you still need to solve it, you can still do it efficiently. You can still do it efficiently by solving the overlap only once. Just remember where the things overlap. So, you're going to say, well, these shapes overlap. They're not squares. They kind of overlap each other. But, the whole thing is covered now, but it's kind of overlapping. But, and what I'll do is I'll paint over everything, but anytime two shapes are overlapping and this one has already been painted, So I don't have to paint this part. I only have to paint this part to get the second shape. Yes? Okay, what are we doing there? What we're doing there is just remembering, right, where the problem has already been solved in a subproblem. I don't solve that again. So you avoid the repeated solution, right? Repeated paint on the same area. You avoid that, you remember that, and then you can solve it. So that technique of solving a big problem by chopping it up into overlapping subproblems such that you solve the whole thing, but the overlaps are only solved once. You remember that, and the term for that is also, some people also use the term caching, right? C-A-C-H-E, caching. Caching is when you solve a problem and you think that, you know, it could be useful again. The same thing could be encountered again. You take the solution and store it away, saying the next time I come across the same problem, I'm not going to try and solve it. I've already solved it once. I'll take that and use it there. So that technique of solving a problem where you say overlap, so you know, break it down into overlapping subproblems, and I have a technique where the overlaps can only be solved once. That is dynamic programming. And the interesting part of dynamic programming, you know, you go to Leak Code and all these other places, so many dynamic programming problems. The interesting part really is not in the recursion, but is in determining what are the overlaps and how can I prevent myself from recomputing the overlaps more than once, and which we'll see in Fibonacci later on. Okay, so here, yeah. No, actually, that is not true, Hana. Yeah, don't, because even though recursion can be used in for dynamic programming, the recursive variant of dynamic programming is called memoized recursion. Okay, memoized meaning, right, I solve a problem and then I take the solution and then I write it in a memo and store it somewhere, so that next time I have the same problem, I can just look at the global memo. So it's called memoized, or some people call it ledgerized. So that is called memoized. However, it's still recursion there, and recursion is ugly, and therefore the same recursive problem, which has, you know, memoized recursion, can be turned into something that does not use recursion as table driven. Again, you know, Fibonacci lends itself to do that, and that's why we're going to be looking at Fibonacci later on, I think. Yeah.
Sorry,
yeah,
I was just thinking of adding what you said to like notes for people not in class.
Oh, I see. Yeah. All right. You can say, I don't know how we can say that. You can say, yeah, you can say, yeah, you can say memoized recursion is a way, memoized recursion is often turned into table-driven dynamic programming. No, memoized, not memorized, memoized, 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 memoized. Memoized recursion is, you know, I think it's just, yeah, memoized recursion, yeah, right, is often implemented non-recursively using dynamic programming. And then, you know, and then you can use Google to find more information about this. Okay, and this is not going to be tested in your final, you know, dynamic, what is, and you can also put a note on the next line saying, right, programming on the next line, you can say you can say not tested in your final, but something interesting for you to Google, right? Not tested in the final, but something interesting to Google and find out more. So that is what dynamic programming is. You know, when people say, oh, you know, especially when you go and you're preparing for interviews and all, people say, oh, do you know dynamic programming? Do you know this? And there's no reason to get, you know, spooked by that. Dynamic programming is nothing but just memoized recursion, just done in a non-recursive way by maintaining a global table or something where you store the cache values. Now, pre-computed values, just store that. That's all. Okay. All right. So here's what we'll do. Now, now we don't need that bad recursion thing anymore. We'll try and solve some simple problems and gradually go and try other problems. Okay. The first thing we're going to try is the standard thing that every class you ever do anywhere in the world. Okay. Hey, I want to learn about recursion. They'll tell you, all right, let's do this. Okay. This is the simplest and easiest problem. We're going to try, go to the place after line 21 and hit enter. Right. One more time. And say int factorial, okay? Factorial, right? Calculating the factorial of a number is the archetypical recursion problem that every professor, I think, I know, right, has given to their students at some point, okay? So, and everybody know what a factorial is? Does everybody know what a factorial is? Raise your hand if you don't know what a factorial is. Everybody, so I can assume that everybody knows what a factorial is? Yeah, good. Right, so factorial is just 1 times 2 times 3 times all the way up to n. So here's what we're going to do. Let's put a comment on, go to line 22 and hit enter, line 22 and hit enter. Blank line above that, right? And say recursive version of the factorial function. And then within parentheses, you can say, this is bad, right? This is bad. And discuss why, right? And this is bad, discuss why in the forums, maybe, right? Discuss. Okay, good. So here, how can you do factorial recursively? So can someone tell me, no, not Hannah, maybe I think Hannah probably knows how to do this. Okay, so let's say someone else, okay? Someone else, why don't you call out the code? Because these are all simple, right? These are simple things. So someone, so not Erica, not Yu Yang, someone who's not been, coding or on screen before, recently. Everybody's done this before, but someone who's not had a chance to code recently, take a chance at calling out the code for this recursive factorial function. It's 2 lines, right? It's 2 lines of code, maybe 3 lines. If you do things slightly differently, 3 lines. But this function should return the factorial of n. Let's put one more comment on after line 23, in case there are students who don't know what factorial is, okay? You guys know, but maybe people who watch the video may not know, right? Factorial of n, factorial n, say factorial of n equals 1 times 1 star 2 star 3 star ... star n. No, that way you'll have to write n minus 1 and all, it's pain, right? So just start from 1, then that's cleaner, easier to read. ... and then you can only say n at the end. No, you need n, star n, all right. So that's why it's easier, because if you said n, start from n, you have to go n minus 1, which is a pain, right? So that's what it is. So can someone say, can someone implement this? Can someone implement this recursively, right? Using what you know from recursion so far, other than the people that I called out, someone take a stab at it, okay? So anyone can. So I think Elijah can do it, Karthik, Simon, Matt, Rouge, right? Anyone can call out the code, and then Hannah will type it in.
I think I'll try it, since I think it's just 2 lines.
It is 2 lines, isn't it?
Yeah, I think it's 2 lines.
All right,
If n equals to 1, return 1.
You got to get out of the habit of putting parentheses around.
Else return factorial n minus 1. N times factorial n minus 1. Yeah.
Okay.
I think
Thank you, Roger. All right. So so let's clean up the code a little bit. Okay, Hannah, put spaces on both sides of the equals. Yeah, there you go. On both sides of the operators, there. N double equals 1. So I think it looks nicer.
Should we make it like if n is greater than 1?
Yes. Very good. Thank you, Sabrina. Okay. See, that is something that I would only expect someone with a little bit more experience in programming to say. Okay, and that is an example of defensive programming, right? And you'll see why that is. Okay, so suppose what happened here. Sabrina says no. Sabrina says if n is greater than 0. If n if n is less than or equal to. Is that what you typed, Hannah? No, less than or equal to, not equal to, less than or equal to, right? So that's what Sabrina said. Sabrina said, if it is less than or equal to 1, return 1. Otherwise, it's And why is that important? Why is that statement super duper important? Okay, it's like super duper important. What Sabrina just made, that change is like super duper important. It is critical for the functioning of this method. Okay, but even otherwise it'll work. But there are some cases where it'll just crash the program, right? It'll crash the program altogether. And experience will usually tell you, oh, that's why it crashed the program. Well, if we are defensive here, it wouldn't have crashed. So why is it important?
Because if you're doing n-1 and then you put 1, it'll be 0. But then if you put like -1, that turns to -2.
Yeah. Okay. Because our n is an integer, right? It's not unsigned, so it can go negative. So once it goes negative, it's never going to be equal to 0, and it's going to keep on decrementing. -1, -2, -3, -4, and so on, all the way to -infinity. And you have there's no way. And well, actually, it'll go to -infinity and then roll over and become positive infinity, right? And then it'll start decrementing from there. Not infinity, obviously. Positive, 21 million or 21 billion, the number that Sabrina said before, right? It'll go all the way, roll over, and then from there it'll start decrementing. And when it hits 0, that's when it'll stop. It's incorrect also. So that is the reason why we do this. Okay, now you can actually call the method too. You can call the method from, in fact, in main, why don't you do a loop, like, it's practice again, not because we're trying to learn these things, it's just practice. Do a loop of a user interaction loop, and I'm not going to talk. Okay, you guys have 2 minutes. So Hannah was going to do a user interaction loop where you say, what you're going to ask the user, what number do you want the factorial for? They're going to type it in, and then you're going to calculate the factorial and say factorial of n equals this, right? And you do that in a loop until the user hits Control C is fine. So you can do an infinite loop if you want. Yeah, and don't do while one. Okay. Hey, that's a bad practice, by the way. Okay, it is correct. It is correct, Hannah, but it is bad practice in C++. And the reason it is bad practice is because in C and in C++, 0 is treated as false, and anything that is non-zero is treated as true. And it is a powerful thing. You can do that. I've seen lots and lots of code. I've written code too, where like Hannah said, while n and so on. It's not a good idea to do that, because C++ gives you explicit booleans. Yeah, it gives you explicit booleans, true and false. Now, it's only explicit visually. Internally, C++ will convert it into 1 and 0, right? Internally, it's going to be 1 and 0. It's not going to be 1 bit. It's one whole, So, but still, it is better to say while true. Right. So while true, yeah. Welcome to, and what is your, yeah. Well, if you're going to print a welcome message, the welcome needs to be done only once, right? Before the while. So you don't need a welcome message. You can just say, see out, what is the, yeah, what number do you want the factorial for? Everybody okay with this so far? Yeah? Because Hannah's just typing. I want to make sure that everybody's on board. And put a space after the question mark. Put a space after the question mark. Put a space after the question mark. And also input, put a blank line after input, input, blank line after input, and then say a string user input, right? String user input. And why am I doing that? Okay, user input, semicolon, enter. Okay, right? Now you have a string, and so why do we need that? Because you want to use get, you're not going to be doing cin left cin into the variable. You're going to get in get line into user input and then convert that into your number. It's always a safer way to do that, because when you do that, you're not going to be messing around with the actual cin, because get line is the only thing that can talk to cin, and it knows how to do it properly. Because you're just getting everything on that line string, right? But if you say get me an integer, but the user actually types in a string, that means you're basically screwed up cin globally. From cin is global, right? You didn't make cin was given to you when your program started, so it's a global variable. You can say, take a global variable and screw it up, and everybody will have broken variable after that. So that's why when you take a global variable like cin and cout, you have to use them very carefully, saying I'm not going to mess it up by saying, oh, this is a cin pipe, and I'm going to read an integer from it, but what's coming in is a string. Okay, that'll screw it up. So that's why we want to get line and then convert it. Everybody okay with what Hannah's doing? We've done this a few times before. That's why I'm not gonna interrupt. No, you can't do, oh, you want to do, no, let's not do A to I. Let's not do A to I. So do I string stream, which is usually much easier. So you want to go all the way to the top and hash include S stream, hash include S stream. After IO stream, say hash include S stream.
Like that?
Yeah, like that.
Okay. Well,
I think that's what it is. Okay, we'll find out if that's not right. Okay, and then in your get line, where's your get line thing?
where is it? Oh, here it is. Yeah.
There you go. So there on the next line, you can say O string stream, O string stream, output string stream, O string stream,
Like,
O string, O string, string, stream,
oh, stream?
strings, no, string stream, string stream.
String stream?
Yeah, space. And we need a variable name. We'll just call it OSS, OSS for now, right? OSS, open parentheses, user input. Right, semicolon. On the next line, you can say OSS, right shift into input. Right, and you put a comment on that line further in, yeah, comment there saying safer than doing, C in greater than input. No, yeah, right shift. Right, and you can also say discuss why in the forums if you want. Okay, you can say discuss why. Okay, so now you can call your method and do all those things that you wanted to do. You can call your method and print the output. Yeah, go ahead. Ah, I see. End L, right? And put spaces on both sides of the shift operators. Great. Okay, so now if you run this program, we should see that behavior. Yes, it's going to ask us for a number and it's going to calculate the factorial and print it out. Yeah.
Oh, shouldn't
So-
we do like an end condition if we want to exit it?
Oh, you don't have an exit? No, I was thinking just hit Control C because you got a
Okay.
prompt. Yeah.
Yeah.
Because this is just something. It's just a driver for us. It's not like a profile.
Yeah.
Good. All right. So if you run it now, you should be able to see your factorial method in action. What's going on there? No match for operator. O string stream. Oh, I'm sorry. It's I string stream, input string stream. Yeah, and call it ISS instead of OSS. No, you call it ISS also. It's not the name of the variable. Change the name of the variable to ISS. On line 41. Yeah. And next one. Yeah, run it now. Okay, now you can type any number you want. No, not big numbers, okay? Because factorial of big numbers take a long time to, big numbers. Okay, so type 2, maybe you should get 2, right? 2, 3, okay, 6. You get 6. Oh, well, output is 2. Something is wrong. Something is wrong there. Why is the output? All right, so we got to debug this. Okay, 5. Okay, so it's actually going for 1 less always. It's going for 1 less. So it's so you got to debug it. So I would prefer if HANA doesn't debug it. Okay, HANA just has the code up there. Someone else other than HANA should debug this problem. Why is it not printing the correct factorial? Right? So this is testing. We're testing it. Why is it not printing? What do we need to change? It's probably just one simple change, very simple change. You got to make that change and say, get it to work correctly. Three. So if you call it with 3, you get, and it goes factorial of 3. There'll be 3 times factorial of 2. 3 times 2 times 1. That should be 6. Oh, factorial of 3 should be 6. Why did it print factorial of? Oh, yeah, and let's clean it up also. Get rid of the else. You don't need the else there because it's a return. Yeah, stop it. Yeah, kill it. Get rid of the else. It's exactly the same logic, okay? And yeah, great. Okay, now why is it?
I still think it should be factorial minus 1. I think we should not change the value of p. Perhaps.
No, that shouldn't make any difference. I don't think. Try 3. Oh wow! Hang on. Okay, wow. Okay, I think I know what happened here. Okay, Hannah, and it's a very good. I think I know what happened. Okay, I know what the issue is, and I don't expect any of you to know the answer. Okay. However, if you do know the answer, it'll be cool. It'll be cool. Okay. So tell me, can someone tell me what is the answer there? Why did n-1 work? What is Rouget? Rouget, were you the one who said that?
Yes.
Yeah. So what is it? Why is it that Rouget's suggestion worked and the n-minus that Hannah wrote did not work? If you want me to tell you the answer, I can tell you. But it'll be cool if you can think about it for like 5 or 10 seconds and see, do you have an idea, right? Some rough idea as to why that happens. No?
Is it because the minus n like actually changes the value of n? Or if you just call it with n-1, like the value of n is still the same?
Yeah, you're right. And minus changes the value of n. But why? But you see that it's n times factorial of n-1, right? No, n times factorial of minus n. So you got n, which is 3, times factorial of 3 minus. So 3 times factorial of 2. Yes? But inside the function, inside the recursive call, n is going to be 2. That value is going to be 2. So by looking at it, it seems obvious that it should work. However, it didn't work. And so the reason for that is because the way the code is written with n-, is not something that we should generally use for good programming style, because we don't know the order in which the 2 operands are going to be computed. Now, I don't know, I don't expect you to have known this before, but if you have, it's in the C++ standard. If you have an expression which has, A equals B plus C, and B is an expression and C is also an expression. So in order to find A, you need to first calculate B and then calculate C and then add them together. It's possible, isn't it? You could write code like that. However, in the C++ standard, when you say A equals B plus C, does not specify that B should be calculated first and then C calculated. It doesn't say that. Therefore, technically, C could be calculated first and then B calculated next. And that is still a valid C++ program. And that is why when we wrote it the way that Hannah wrote before, it's actually misleading, because that is not the way the compiler would see it. The compiler will look at it and say, well, you know what, there's 2 things I need to multiply. Let me calculate the bigger one first, because I want to get the big job out of my way first. So I'm going to do, factorial n-, first. And by that time, when it comes to multiplying by n is already decremented, which is what Namrata said. So what it actually ended up doing was, calculate factorial of 2 times, 1. And I think, all right. So the decrementing happened before the multiplication. That was the reason, and it's a very subtle reason. And this is the reason. Something like that could have taken 15 or 20 minutes of debugging later on, right? Depending on where it is, could have, and that is why it's very important to, when we write code, to write it very explicitly and not use minus and plus carelessly. And so that doesn't make sense. I don't know if it was useful, but does that make sense, right? The order in which they're calculated is not specified. When the order is not specified, you can't just use minus and plus without knowing, because you need, and especially when you're using the same variable in many places, right? So now if you say this, does it work? Right now, yeah, excellent. Right, so 3 is 6, 5 should be 120. All right, great. Now, if you try a big number, obviously it's not going to work, right? If you try 33, and why is that? Because the factorial of 33 is a big number. It's bigger than what you can store in 30, in 4 bytes. And that's why you get, junk after that. It goes negative and so on. Okay, now, all right. So we want to do one more recursive function, which is, again, a simple function, and you are going to write this. Okay, I'm not going to be involved at all. So the sum of the first n natural numbers. In fact, let's make it easier, okay? Because you've already done arithmetic progressions in quest number 4 or 5, 2 or 3. So one of these quests you did arithmetic progressions, arithmetic and geometric progressions. Did you do APs and GPs? Yeah, calculate. Yeah, you have to return a string with the first 5 terms of a geometric progression or arithmetic progression. Yeah. Okay, so let's do that. Because again, it's an iterative approach. And so let's go to line 30 and hit enter. Go to line 30 and hit enter. Yeah, now start a comment there. Comment saying iterative version of iterative, IT, not iterative. Iterative version of let's just say, we'll keep it simple, right? Because we're just focusing on recursion and not AP and all, right? First n natural numbers. Of the first n and numbers, natural numbers, not, Natural numbers start at 1. Whole numbers, no, actually, natural numbers start at 0, right? Whole numbers start at 1. Okay, so first n natural 0 plus. So let's say whole numbers, okay? Because adding 0 is not going to make a difference. Say whole numbers. So whole numbers, and then within parentheses at the end, you can say 0 plus 1 plus 2 plus and so on, ... and then last thing should be n. Just like for factorial, instead of the times, you're going to use plus here. 1 plus 2 plus and so on. Up to n, yeah. Right, on the next line, you can say, oh, no, not iterative. I'm so sorry, Hannah, right? It's recursive. On the next line, you can say recursive statement of the problem, okay? And it's always useful to have a recursive statement of the problem before you go and code it, okay? And of the problem, on the next line, you can say sum of n, right? Sum n equals, right? And then this part, you're going to just type in comments, okay? You're going to type in comments. What is the sum of n going to be? Right? And then not Hannah, right? Not Hannah. One of you should call out the code, and Hannah will type. Hannah, you're okay with just typing, right? And someone calling out the code, good, right? So Hannah's not going to type, but however, someone should complete this line 34. Someone should call out the line, complete it, and then Hannah will start the function. And again, it's like 2 lines, right? 2-line function. You're going to find the sum of the first n natural numbers in that and return. That's all. Very simple. 5 minutes maybe, right? We have a lot of time. We have almost an hour left. Okay, so we have time to do Fibonacci and all these other things too. Okay, so please, I'm just watching. Okay, I'm not. If you don't want me to watch, I won't watch. Okay, I'll just turn the laptop around for 5 minutes. So fill in the comment and then start implementing the function. It's got to be very similar. to what the factorial is, except there are slight differences, okay? And do it, and then verify it too. And you have to change your main method in the driver and say, what number do you want sigma n for, and so on and so forth, okay? And run it in the loop, and let's make sure it works, okay? Now do it. I'll give you 5 minutes. I'm not going to be in front of you, okay? So now maybe this will help. Just implement that. It's very simple. It's only 2 or 3 lines. So do it on your own, someone other than Hana, and then we'll take it from there, okay?
Yeah, so if n is less than, less than or equal to 1, wait, that's 0, 0, right? 0 return 0. Do we need the curly? Yeah, because we can just do the next line, because that'll be like the, because wait, yes, or did he want zeros? Did he want, is the 1 the smallest number? Maybe 1, I guess. Yeah, and then return n times sum of n plus 1. Oh yeah, this one. Would it be n plus 1 because we're adding them, or oh yeah, no, it is n minus 1. You're right. Sweet.
Actually, if we did that, I think we need to do a for loop to kind of increase the value of n. Right? No, maybe not. I don't know, because
I think we're still
did
kind
like
of,
some n minus, or I don't know, maybe that would work too.
because I think we're like just picking that. It's kind of like, well, what the intention was like to pick that last number, and then it's like add all the ones underneath this.
Yeah, no, yeah, I get that, but somewhere, I mean, I think that works, but I think somewhere in there you need something that increments the n, because if you put like 3, it'll be like 3 plus 2 plus, oh wait, I think I'm reading this wrong.
I think it's just going to be recursive to the bottom, because I think like part of recursion is to not like loop, or at least that's how.
Oh wait, yeah, I see what you're saying.
Yeah, because all these you technically could just use a loop for to like do that, but I think it's like in place of a loop. I'm also like not super great at recursion, so anyone else feel free to
Actually, I think this might work for doing it recursive.
chime in.
Yeah, I think, like if it's like we called it with 3, then it'd be like 3 plus sum of 2, and then sum of 2 would be like 2 plus sum of 1, and then since 1 is our base case, it would return 1. So it'd be like 1 plus 1, and then that like returns back. So it'd be like 3 plus sum of 2, which we just got was 2, which should be like 5. I think that's how it would work.
I think so too.
Would you guys like me to run it?
Yeah. Yes.
Is that doesn't seem correct. Oh, wait, is it? It is. Wait, yeah, it is.
Actually, wait, is
that correct? I think it is. Wait.
Yeah, that's right.
Okay.
This is a side note. So if you're using any of these recursive functions, we would have to include that CMath library for it to work.
Actually, I don't think you're using CMath.
Oh, we are?
No, we're not.
Oh, okay. I could have sworn that factorial falls under that.
So CMath has a factorial function that just does it itself. So you could call like factorial of like 7, and it will do all the factorials, but we're making our own using recursion.
Yeah, I don't think this is a really great way to do the function though, because it like uses up a lot of memory or something. because it
Yeah. I feel like it's probably more efficient than like our first iteration of like factorials when we didn't know how to, when we were just looping, maybe. Guess we'll figure out memory allocation in 2B.
yeah, I'm still really confused about the memory stuff.
Yeah, me too. I like try to think about it every now and then, like, huh, I wonder how much memory I'm using. Like, is this actually like it's the clunky way to do it or the moderately efficient way?
I remember on some of the tests, on some of the quiz, or no, on some of the quests. Sorry, I'm messing everything up. It was like there's a deconstructor, and I still have no idea what that does. I think it just like deallocates.
Past quiz, or I mean quiz quest, the pet one, I'm really stuck on.
I think on quiz 9 or quest 9, there's like, I don't know. The professor like said that there's like, you don't need to do memory management, but like you should. And I think I just did it without memory management because I was really confused.
Yeah, that's I was looking at because I was stuck on like quest 6 for a while and quest 7 and 8 stuff came up too, and I was like, ooh, memory leaks. Don't know what those are yet, but I'm gonna find out. You got it working, Professor.
Yay, okay, hang on. All right. Great, let's take a look. So where's some, oh, some, all right. N less than 1. Yeah, okay. As you can see, it's very similar to what you had in the iterative version. Yes. And it's all great. Okay. All right. Now, now that you know, can you do the same thing? Can you do exactly the same function iteratively? It's for some. So rewrite the same function. So copy the copy the whole thing from 33 to 41, paste it, and then let's call this iterative version of the sum of the first n natural numbers. Yeah, make it iterative, and just change the function also. And you can get rid of you can get rid of that line saying iterative statement of the problem, because we don't have an iterative statement of the problem. And call the function, I don't know, call it something else. Some underscore iterative, yeah. Yeah. No. Hey, this is the second time you're doing this. Is there a programming language you're using in which the two tokens are swapped? Because even in Python or Java, it's less than then equals, not equals less than.
Sorry, I just haven't programmed in some time.
All right, okay.
Wait, it's wait, it's okay, it's gonna be like that.
Yeah, there you go. That's the right thing.
Okay, so we're gonna do n plus equals I, return n.
Oh, hang on.
Right.
So let's and get rid of the parentheses around n also. Return n. Return n.
Right.
Wait a sec. So I'm running the logic of that for loop in my head. Everybody else should also be doing that, and making sure that it works. And if it doesn't, you can this is time you say, hey, I don't think that'll work, and Hannah will change it. Okay. So I'm running the code in my head, so you should also be doing the same thing.
Oh wait, no, wait, that does not work. Oops. Okay, we can make like a int sum. There.
And you don't need the braces for the for loop either. And put a blank
Mhm.
line before the for loop so that it's separated from the declarations. All right, so will that function work? Everybody should run it in their heads and tell me yes or no.
I think so.
Everybody else? I guess you guys are saying yes implicitly. I don't know. All right. However, let's try and do this the other way that Hannah said. Hannah was doing before, which is adding to n itself. Okay, adding to. Can you do that? Can you do it by adding to n itself?
So should I delete this?
Yeah, I can delete that. So I wasn't planning to do it that way, by the way, right? After you started doing it, I said, oh, all right, let's do it this way. This is actually cooler because it's a select challenge. If you want to do it with n, the challenge that Hannah ran into and say, hey, I got to change it. No, but it's possible to do it that way too. So how would you do it?
I think you could do sum under the for loop. Sum equals n.
No, there's no sum. There's no sum.
Well, and well, wouldn't you just replace the word sum, so n plus equals I?
But n is being used in the for loop to determine when it stops.
And then I guess you could like, instead of incrementing I, like make it start at n and then decrement I.
Oh, actually, you know what? I just realized it's not possible.
Okay.
You need another variable. You need another variable, but it's worth, right? It's worth trying it. It's worth trying to find out what the challenge is. So try it.
I think in like Python, like when you do the for loop, it keeps like a constant value of whatever you're trying to, like the end value is.
So,
So when you change,
exactly, in some other languages you have this implicit variables and things thrown in for you that you cannot see, but not so here.
Wait,
so,
Professor?
Yeah.
Don't both these like functions have the same running time? Is there like a way to calculate like the memory usage?
No, they don't have the same running time. Okay.
Really?
In fact, recursive functions are usually a lot worse, than iterative functions. If you have the same functionality iteratively and recursively from a computer, from a professional, commercial software point of view, you should never use the recursive function. You should always, because the way you think about what we said before in the previous class, when we talked about how functions are called. When a function is called, lots of things have to happen. Yes, because calling a function is not simple. When you call a function, you need to remember, right? You need to say, well, I'm going to go off and do something, but after that's done, what am I going to do? I got to come back here and resume. So I got to remember the return address. Yes.
Yeah.
So that's already one thing that I have to remember every time I call a function. So if that function calls another function, then that function has to remember the return address. And so if that chain is progressing like that for a million times, there's a million return addresses that need to be remembered, because they all need to be, on the way back, you need to go back in reverse. Yes.
Yeah. So like the memory for the recursive one is a lot higher. Isn't like the O value both of them n though? Like.
Yeah, they do, but they don't end until the called function has returned. So if A calls B and B calls C, A is still there. A hasn't gone when C is running.
Oh.
So A calls B, right? They're all still, they're all in cryo state. They haven't died. They're just frozen, saying, well, when you're done, I'm going to wake up. So how many of those can you afford to have? So when you recurse, there's always, it is called the recursion overhead. Some people call it the stack overhead. Okay. And the reason it's called a stack overhead, is because all these return addresses need to be stored in some place in which they come off in the reverse order. Yes. So what's the best place to store something where it's always the reverse order, meaning the last thing to go in is the first thing to come out? That's a stack. And we're going to implement a stack, right? We'll implement a stack very soon. Maybe today or maybe next class, we'll implement a stack. And a stack is essentially the data structure that you need, which is also the data structure the runtime system itself uses. When the computer is going to use a stack, you don't see it. When you have recursion, there's a stack built in there. a stack all in the background that is going to keep track of all the return addresses. You know, oh, it's recursing, so I got to remember where I need to come back. Oh, that's recursing too, right? This is recursing. You got to remember all those things. Those are stored on the stack. This is the stack overhead. It gets huge sometimes, especially unchecked recursion. That's why a program crashed. The first program that we wrote was unchecked recursion, right? And the program crashed. And it crashed because it ran out of stack space. Every program, when it starts up, gets a free stack that is fixed size. It's really big. It's 200 megabytes of stack space or something like that. It's possible to find out. We're not going to waste time trying to find out. It's possible to find, but typically when your program starts up, you get a lot of stack, 200 megabytes of stack or something like that, right? And 200 megabytes, that's what you use for when calling functions, when recursing deeply, and so on. That stack is used up. But 200 megabytes is nothing compared to the overall memory you could have in your program, right? You can have 32 gigabytes of memory on your computer. So the stack space is very small. So you can run out of stack space really quickly. Even though it's 200 megabytes, you may not see it, but in large programs, you could run out of stack space in recursion. Whereas if it's main memory, it'll keep going on and on until the entire memory is exhausted. Very unlikely to happen in many modern computers. That is why recursion should be avoided. However, in certain places where you are confident, this is a super duper important part, okay? When to use recursion, when not to use recursion, many programmers don't even seem to know. Even professional programmers, I've known, right? So when I interview people, they say, but why did you use recursion there? They don't know. They don't. It is important to know when to use recursion and when not to use recursion. You will use recursion when when there are no overlapping subproblems, and well, that's a secondary issue. You will use recursion when you know the recursive depth is bounded. Okay, you know for sure that is never going to have unbounded recursion. It's not going to recurse 1 million times. I know for sure that I'm using a tree, right? Let's say I'm using recursion to fiddle with a tree, and a tree goes like this, right? Everything branches into 2. So it's exponential. The growth of the tree is exponential. The number of leaves at any level is 2 to the power of that level, isn't it? So at level 1, you have 2 leaves. At level 3, level 2, you have 4 leaves. Level 3, you have 8 leaves. Yes? If you draw out a tree. Tree, I don't know, a tree is basically one node, has 2 children. Okay? That's at level 2, 2 children. Level 3, well, let's call that level 1. Level 1, 2 children. Okay. Level 0 is a root, 1 child. Level 1, 2 children. Now level 3, level 2, right? Each of those 2 children will have 2 children of their own. So we have 4. So essentially, if you go to level n, you have 2 to the n, 2 to the n, 2 to the n leaves. So now, so obviously, when I'm doing recursion there. If I know that it's not going to recurse past, I don't know, 5 million nodes or 5 million, depth of 5 million, right? Then I'll know how to use recursion. Now, why is it that recursion is good for trees? Data structures that branch out like that, okay, like trees exponentially, recursion is good there because the number of calls you're going to make is bounded not by the number of leaves, but by the depth of the recursion. Right? So I call it once, it goes to level 1. And then each of these guys is going to call it once, it'll go to level 2. Each of those guys is going to call it once, it goes to level 3. So even though the data size increases exponentially, right? The data is the number of leaves. The data increases exponentially. The depth of the tree does not increase exponentially. Yeah? In fact, it is easy to show. The depth of the tree is the log of the number of leaves.
Right, so
it's
the
a
running
logarithm.
time is it n log n?
No.
Is it just
It's
log
not
n?
n log n, by the way. Yeah, it's not n log n. Let's not talk about running times yet. Okay. So what happens there is recursion is a good candidate there because I know that no matter, even if I get huge amounts of data, when I store that in a tree, it's not going to recurse past, I don't know, 1,000 levels, 2,000 levels. You have it in your head, right? Because if it goes past 1,000 levels, I don't even have enough heap, and the computer is definitely going to crash. So certain cases, you know for sure, when processing graphs, trees, and so on, you know for 100% sure that it is never going to recurse past, more than 5,000 deep or something like that. Those are the situations where people can use recursion. So when you're doing an interview and all, and so people say, why do you use recursion there? the correct answer there is I can use recursion there because I'm confident that the depth will never exceed 5,000. Depth will never exceed 32,000, right? So that is the only reason to use recursion. The other reason to use recursion, which is what newbies tend to do, is because recursion is prettier. Right? A recursive solution, if you look at it, at the end of the day, it's actually prettier, isn't it? It's nice and tight and compact. It's, you know, and it's also easy to understand. Because you say, well, you know, solve a big problem. I know how to solve a big problem. I know how to solve a small problem. So you just need to put stuff together and I solve a big problem. So recursive functions are easier to understand and write, and they don't take a lot of space. So it's good for humans. However, the computer says it's the opposite, right? Computer says, well, it's good for humans, but it's really, really bad for me, because when you do recursion, I got to remember a lot of things. I got to remember the stack. I got to return the return address, all these things. So what is good for humans is actually bad for the computer. So recursion is not good for the computer. And in fact, when in modern computers, always look at recursive code and see if, hey, this is recursive code. It's easier for the human. That's why humans wrote it recursively, but it's not good for the computer, CPU. So I'm the compiler. I'm going to translate between humans and compilers. So not only am I going to translate the meaning, but I'll also make it easier for the compiler to understand. Yes, just like, you know, a translator says a really complicated phrase in English, needs to translate into Chinese. Okay, and they say, you know, I'm just not going to translate the exact words, like, you know, yeah, take an idiom, right? So my favorite idiom that I've used is, you know, Namrata flew to UCSB in her car because she was late for a lecture or something like that, right? Flew, right? If you talk to another English speaker, they'll know. Oh, Namrata went really fast in her car. But if I want to say that to a Chinese speaker, they can translate that literally. Because, you know, he flew to a college may mean something else in Chinese or some other language. So they have to understand the meaning and translate that into a corresponding idiom in the other language, in the target language. Meaning that it's not just a straight translation because they used an idiom. I still have to use an idiom, but it's got to be an idiom in the native language, right? So that is the kind of translation that modern AI chatbots and things will also have to do, right? Because if you say, you know, I got this thing, I got to translate that into Chinese or some other language, it won't just be a word to word or sentence to sentence translation. It'll actually be a meaning to meaning translation, meaning that, you know, even phrases might be different. It may not be exactly what you said, but it actually conveys the exact meaning. So that is why the compiler, which plays the intermediary between the humans and the CPU, will say, well, you know what, this is easy for humans to understand. That's what the humans need to understand. It's bad for the compiler to run, the CPU to run. So in the process of translating the recursive code, I'm going to try and see if I can convert the recursive code into iterative code in the compiler itself. It's really cool, isn't it? Didn't used to be the case a long time ago, very long time, bad old days of compiler design. You know, recursion was always recursion, but people started figuring out cases, special cases of recursion that can be converted from recursion to iteration by the compiler. Humans don't have to worry about it. Therefore, humans can still write clean, readable, easy to understand recursive code, and the compiler will translate that into iterative code for the CPU. So the CPU will still be efficient, and the humans will still have readable code. How cool is that? Okay, the compiler plays the intermediary. And that didn't used to be the case. And of course, we shouldn't take it for granted that everything that we write that is recursive will automatically be converted to that. That's not the case, okay? That's why you need to have experience in programming. So you know, you'll get a feel for what are the kinds of things the compiler will automatically do for me. So I don't have to do it. And the compilers today do a lot of things for humans. And that's why it's important to know all the nitty-gritty details of these things so that we can still continue to write our programs in the most human-friendly way that is easy for us, rather than, because I know even, you know, a few years ago when I was teaching CS2A, lots of students used to write assignments saying, well, I'm doing it this way because it's faster. I'm saving a few extra cycles here. I'm going to use a you know, integer instead of a float. All these things, they make these lower level optimizations in the code. That is history. Okay, anyone who does that these days is probably a relic from the past, meaning they haven't programmed the last 20 years or something, right? Because in the last 20 years, compilers have evolved significantly, meaning that humans can write human readable code. And the compiler is responsible for turning that into what is efficient and useful for the CPU to run. And that is why when you write a recursive code and all, you just keep this in mind, saying, oh, the compiler can do all these things. I can just, but still, I will write it like a human. And then the CPU will have AI built in. You know, in a few years, CPUs will have AI built in too, which will do, you know, the right kind of optimization, pick out fragments that are prime candidates for optimization, and turn, you know, recursion into. And in fact, the code that comes out may not even be similar to the code that you've written. Today, you can take assembler code that has been generated from your C++ program, and you can do a mapping. Hey, yeah. Okay, this is the assembler code generated by the compiler that the CPU will run. This is the program that I wrote. Hey, yeah, this fragment is that fragment is that. You can do that today, mostly, right? You can do that. But in a few years, you're not going to be able to do that, because what you write may be completely different from what the compiler generates for the CPU. You can't even do a direct mapping anymore. But it'll do the job because it would have figured out all the regular transformation, predictable regular transformations, right? And it'll do it automatically in the background. So that is why recursion is bad, and it should be avoided as much as possible. But still, programmers will do recursion initially to get the logic right. And once they have the logic right, they'll take a look at the program again. Say, well, now it works. I'm going to try and convert all those recursions into iterations, because then it's going to production now. In the production system, it's got to be fast, because it's going to be in the hands of users, and they can't tolerate slowness. Yeah, so that is the reason why. All right. So now, do you guys have any questions? Was there anything else I needed to say? Iterative, right? And some. Yeah. Okay. All right. So I think this was simple enough. Now let's try and do Fibonacci. Okay. Let's try and do Fibonacci, which is going to expose the issue with right. So let's try Fibonacci. So and say long Fibonacci, okay? Because Fibonacci, as you know, the numbers will get bigger and bigger. In fact, even a factorial should have been long, but doesn't matter, right? This is a Fibonacci, long Fibonacci. In fact, may say unsigned long, because you know let's not waste that one bit, right? We can use that entire 4 bytes for our numbers, unsigned long, right? Say unsigned, change the long into unsigned long. And by the way, unsigned long is exactly the same as size t. There's some in the include files you have. There's a hash define or something that says, oh, every time you see unsigned size t, it's the same as unsigned long. So you can change that unsigned long into size t, right? And then you can put a comment, or you know, leave it there and leave it there and put a comment on the right side, or put a comment on the right side. Unsigned long is the same as size t. Yeah. All right. And I put a blank line above that too, so to separate it from the previous method. Right now here, but after that comment, one more, okay, and say fib n recursive statement. Say recursive statement of Fibonacci, and then on the next line you can say fib n yeah. All right, and then you can say equals, fib n equals, what is it? Fib n minus 1 plus, go on.
Fibonacci is like, it's
every number is the sum of the previous two numbers.
okay.
So Fibonacci of n is, yeah, that's right. Okay, so that is, however, for recursion, it's just so cool that we are doing this now. Is that enough? Is that enough for us to do the Fibonacci function? Go ahead and code it up recursively, right? Yeah, unsigned long n, code it up.
So we need to have our exit point, which is
Yes.
okay, wait, when does the sequence start? It starts at like 1.
I think it starts at 1. Yeah, I think it starts at 1. So you can say if n equals 1 or 2, right? If n equals 1 or 2, you can return 1. In fact, if n is less than 3, you can return 1. If n is less than 3, you can return 1. Yeah. Because Fibonacci of 1 is 1. The first Fibonacci is 1. The second Fibonacci is also 1. The third Fibonacci is 2. Yes.
Turn 1.
Yeah. No parentheses around the 1.
Yep. Sorry. That is bad habit.
Technically, you can have parentheses. Okay, the compiler won't complain. It's still correct code. It's just aesthetic. Most programmers I know don't do that. Okay. All right. So now you can say, right? So now put it in. Now, however, okay, well, you also need to augment the comment you have on line 55 on the next line, because the exit condition is not there. With just those two lines,
Oh.
it doesn't. On the next line, you can say fib 0, fib 1 equals 1, fib 2 equals 1. But those are the two base cases. Fib 1 equals 1, and then put a comment there. Yeah, you can say base case 1, base case 1, base case 1, base case
Wait,
1.
sorry, how do you want me to write that?
No, right there after the one
here?
comma. Yeah, base case comma, base case 1. Yeah. On the next line, you say fib 2 equals 1.
Fib 2 equals 1.
That's a base case. So you have two basis cases here. So which means that it can terminate in two different places. Yeah. Okay. Now you can say, return fib n minus 1 plus fib n minus 2. Yeah. And no parentheses. Yeah. There you go. Fib n minus 1, fib n minus 1.
Fib n minus 1 plus fib n minus. Don't we need to do n plus?
No, why would you do n plus? Because every Fibonacci number is just the sum of the previous two. It's not the sum of itself and the previous two. Yes.
Yeah.
Is everybody okay with this so far? Okay. Now let's add one more comment after line 57. After line 57, add one more comment, right? And say recursive Fibonacci is a bad idea. Discuss why. In the forums, obviously, right? Right now here, so this should obviously work, but it will not work for to try this. Go to your main, change it. Go to your main and change it. Yeah, input. Want the Fibonacci number 4. Well, yeah, fib 4. Yeah, and then no, not the sequence. You want to print the whole sequence or just the target last number?
The fib number, like the fib sum.
No, not the fib sum. It's just Fibonacci. Just say Fibonacci number. Yeah, fib 4. It's fine. It's just testing, right? It doesn't matter. Okay. Now increase the size of the console, and go ahead and type a bunch of numbers. Starting from 1, 2, 3, and so on.
So 1
What is
going to be 1.
2?
2 is 1. 3 is going to be 2. 4 is going to be 4.
No, this is 4 is the previous two numbers.
Oh, previous two numbers.
Yeah, previous two numbers. Okay, now try 20. Oh, all right. Well, hey, that's wrong. Something is wrong here. 20 can be 6765. Is it 6765? Maybe it is 20. Or maybe you say, yeah, try 30. It'll grow fast. Okay, I think I'll try 30. Yeah, it is growing fast. Okay, now try 40. There you go. It took a little while, didn't it? Okay,
Yeah.
Now try 45. Try 45.
Oh, wow. It's taking a while.
Okay, so the time is growing exponentially. This is the time taken by the program to run is growing exponentially with n. So 2 to the n exactly is when I say exponentially, it's not even it's actually exactly 2 to the n. So now 45 is taking so long. So you can imagine it'll come back. 45 is there. You go. It came back. Yeah, but if you try big numbers like 49, you can be sure that it's not going to return before the end of class. Okay, probably not even before the end of today. 49. But however, right, it is not just Fibonacci is actually computable. It is computable. It's taking a long time. And the reason it's taking a long time is because it is wasting enormous amounts of space, right? And computation. In fact, when you calculate a Fibonacci of a large number, 99.9999%, right? Even more than that of your CPU is basically wasted. So a very tiny part of the CPU, the execution is what gives you the answer. Everything else is wasted. Why is it wasted? Why is it wasted? So let's do this. Okay. So let's do. So do you have oh, you don't have an iPad. How do I do this? Yeah, okay. Well, we'll do this. Just do some comments about the Fibonacci code, right? or below the Fibonacci code. Here, hit enter on 63.
Oh.
Enter on 63. Yeah. Now, yeah, let's start a comment. So the above function, the above recursive Fibonacci function, if you want to calculate Fibonacci, if you want to calculate to calculate Fib3, it needs to do, yeah, I think that's a good way, right? To calculate Fib3, it has to do Fib2 and Fib1. Yes or no? Right. Now, suppose I want to calculate Fib5. What is it going to do? Suppose I want to calculate Fib5. It's going to calculate Fib4 and Fib3. Yes. However, because of the way we've written it, how does it calculate Fib4? Fib4 needs to calculate Fib3 also.
It keeps going backwards to all of them.
Yeah, it's got its all, and then Fib3 has got to, so Fib4 has to calculate Fib3 and Fib2, and then Fib3 has got to calculate Fib2 again. So Fib2, how many times is Fib2 already being calculated for just the fourth number? It's being calculated for Fib4, Fib3 here, it's being calculated here, and it's being calculated there. So it's already being calculated 3 times. Fib3 is being calculated 3 times, just for, right? The same thing is being calculated repeatedly. And therefore, if you're trying to calculate the fib of 100, chances are it is calculating Fibonacci of 2 to the 99 times. Hey, how big is 2 to the 99? It's huge, isn't it? So that is why repeatedly, okay? So the way to get around this is to simply say, we're going to use dynamic programming, right? In fact, in this case, dynamic programming is simple, right? This is simple because the overlaps are very simple, easy to spot, and you can do this really cleanly, right? The overlap is basically the entire solution. So in order to calculate Fib3, in order to calculate Fib4, and you calculate Fib2 and Fib3, but Fib2 overlaps with the calculation for Fib2 and Fib3, right? When I want to calculate Fib3, I still need to calculate Fib2. So it's overlapping. So Fib2 needs to be calculated only once. Does that make sense? Because Fib2 is being calculated so many times, it makes sense to calculate it only once and store it. Yes? So you can speed this up greatly by saying, right? So we can speed this. Up greatly by having an array, right? We can speed this up greatly by having an array. Yeah, on the next line. Right? In which we store the results of previous Fibonacci numbers that we have calculated and just looking it up instead of recalculating them. Does that make sense? Now, if you do it this way, you'll find that it'll just zip through, right? Even large numbers, it'll calculate really quickly. Right? So in fact, you can do that now. You can do that now. What time is it? Or maybe oh yeah, it's 10:09. I'm going to leave that as an exercise, okay? So there's an exercise to have an array in which you calculate and store. You can break that line, Hannah. Break that line into 2 lines. It's gotten too long. Right. So exercise is to write a Fibonacci method that is going to use an array to store previous values calculated, so that when you need to calculate a Fibonacci, you're going to look in the array, see if the value already exists. If it exists, you're going to use that. Otherwise, you're going to call it, and then store the value and then use it. That's all. We can do this together if you want. However, if you want to do it, I'm happy for you to do it and share it. And then we will pick up the code again next class. Okay. Next class on Thursday, we'll pick it up and say, hey, you know what? We tried to do Fibonacci recursively, and this is what happens. And then that will lead into our discussion of stacks and implementing stacks and everything. Okay. So, so next class, we've actually set up nicely for next class, I think. So this is what we need to do. If you want me to do it, I will do it now. If you want to, any of you want to stick around and it'll be in the recording also, we can do it now. However, I think it'll also be a nice thing for you guys to try on your own, which is to say, I'm going to use an array of, let's say, start with just an array of 100 numbers, okay? Because I assume that nobody's going to calculate a Fibonacci of more than 100, okay? So assume that 100 numbers, and then you're going to use that array to store intermediate results. Every time you calculate a Fibonacci, you're going to put it there before you calculate the next one. And it's all in the loop, right? So in the loop, you're going to say, I need to calculate these 2 Fibonaccis. Now the first one is in the array. I'll pick it up from the array. The second one, I'm going to calculate. and so on and so forth. In this case, you will actually have, for every number you want to calculate Fibonacci for, I have both of them already in the array. So if I want to calculate Fibonacci of n, I'm going to calculate Fibonacci of 1, put it in the array. Fibonacci of 2, put it in the array. Fibonacci of 3, I'm going to just take the previous 2 elements and put it in the third element, right? Essentially, what you're doing is zipping along the array, zipping through the array. You follow this very carefully, okay? In the iteration, you're zipping through the array, one element at a time. And for each element, you're just going to take the sum of the previous 2 elements in the array and put it there. That's all. Does it work pictorially, mentally, visually? Does it work? Let me know if you can visualize this. All you're doing is that you have an array of 100 elements, okay? And you start off with the first 2 elements being 1 and 1. Just tick 1, 1, right? Array of 0 equals 1, array of 1 equals 1. From array of 2 onwards, all you have to do is just take the previous 2, add them together, put it there. Move to the next one. The previous 2 will be filled. Take the previous 2, add it, put it there. Bam, 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 bam. That way is iterative, no recursion, and it'll just get it done. No recursion at all, right? So there'll be no recursion, and you can do it iteratively. Now, when you get there, when you do it iteratively, you'll find that you don't even need an array, right? Yeah, you don't need an array. You don't need a fixed size of 100 elements and so on. You only need 2 elements, okay? You only need a 2-element array, because to calculate the Fibonacci of anything, all you need is just the previous 2 elements. You don't need all the elements before that, yes? So you only need 2 elements. So it doesn't even have to be an array. So in fact, in your method, you only need 2 extra variables, saying, I want an integer predecessor. Well, let's call it father and grandfather. So for every element, you have a father and a grandfather. You calculate the value. And before you go on to the next element, you're going to make the newly calculated element the father, and the previous father becomes a grandfather. That's all. Does it make sense? So you have an iterative solution, but it's also tight. Now it's really tight. You're not using extra space. You're not using extra variables, right? And it's iterative, no recursion, no stack, and it'll just zip through. And that is the fastest ever Fibonacci you can ever write. Okay, any language that, even assembler, that is the fastest Fibonacci you can write, which only uses 2 values to store the 2 previous predecessors and constantly updates the predecessors, saying, hey, now I'm moving on to the next number. The predecessors have changed. That's all. Does it make sense? Was it clear enough so far? Right? Well, I know and Namrata is nodding her head. And just raise your hand, okay? Raise your hand if this was reasonably clear. We will obviously revisit this, okay? We'll revisit this. Yu-Yang, did you raise your hand? Or was that a thumbs up or something like that? Yeah, okay. All right. Simon, you're looking down. I don't know if you're confused or do you understand this?
Me? Yes.
Okay, good. All right, Elijah.
I'm looking up because like my camera is downside, so.
Oh, all right. Okay, no worries. Okay, Karthik, you good? Okay, good. All right. So all you have to do now is what do we do? You have to implement this method. Okay, implement the method. Maybe share it on the forums. Well, actually, don't share it in the forums, because that is actually the answer to your quest number. I don't know what that quest is, where you have to calculate the Fibonacci. Because if you don't do it, if you do it recursively, you won't get trophies for because it'll time out. Because when you submit the quest for Fibonacci, I'm going to ask you to calculate Fibonacci of 500. Not 500, obviously, right? A Fibonacci of 100 or some big number. And if you do it recursively, it's not going to complete, and you won't get trophies for that. But if you do it iteratively, using just the 2 values, or even if you can use an array, you can use the whole array, but it's wasteful. But it's just 2 values, tight and fast, and it'll just run. And you get trophies for that.
I have a question.
Yeah.
Okay, so because before with array, it was like, so for example, for fib 5 and for fib 5, or we needed fib 4 and fib 3. For the first one with the array, you would have had fib 4 go along and it recursively go, and then fib 3 would just grab the numbers from the array that fib 4 made, like you push back using fib 4 to do that, right?
You have to, yes, you have to. That's I think what you're saying is that if you use an array, you have to go from this direction, not from that direction. You're not going from 5 towards 1, you're going from 1 towards 5. Is that what you're asking?
Yeah, well, I'm just saying like the first part, so for example, like with fib 5, where you're grabbing the 2 fibs or fib 4 and fib 3, then the first The first one is the one that actually like has to calculate. So that'd be like fib4 would calculate all the fibs and make the array.
Mhm.
And then fib3 would just grab from the array and pop out that sum, right?
No.
Is that what you
All
were
right,
saying?
yeah.
Okay, I'm confused.
I'm glad you asked the question, because don't do it that way. Okay, that would be the, you know, it'll
Yeah,
work, but
the
it's not
efficient
efficient.
way.
So if you're going to use an array, this is the easiest way to do it. If I want Fibonacci of 100, say, you know, give me what is the Fibonacci of 100? Don't start at 100 and go work backwards. Okay, start at 1 and say, right, Fibonacci of 1 is 1, Fibonacci of 2 is 1. Okay, what is Fibonacci of 3? This is the sum of the previous two. Put it there. Now, what is Fibonacci of 4? Some of the previous. That way, you only have to look at the previous two elements of the array and keep marching forward all the way up to 100. When you hit 100, you know, right, whatever number you're going to put in the cell number 100 is the answer. Does that make sense?
Okay, yeah. And in that way, like, would you just be like continuously like updating the array, or would it be better like
Yeah, you have to update the array.
Yeah,
you have to because
right.
that's the only way you can get.
Sorry, like not
back. It's
not updating, I mean like replace, like replacing the values and just keep the array smaller, just kind of make this long array of like numbers.
Oh yeah. All right. Do it with the long array of numbers first, okay? Do it. Suppose you start with an array of 100 elements, which means that you'll be able to calculate all the way up to Fibonacci of 100, because each one element of the array is going to hold the Fibonacci of that index. Yes. So start with 100. That means that your program is automatically bounded, saying, this function cannot calculate Fibonacci for greater than 100. However, once you got that working, then you can take that and whittle it down more and say, all right, now I'm going to do Erica's method, where I'm going to replace the values in the array. Now I don't need an array of 100 elements anymore. I only need an array of 2 elements. Because, you know, the array has 2 elements, and the first element is the grandfather. The second element is the father. After I've calculated the next descendant, I'm going to replace. The descendant becomes a father, and the father becomes a grandfather. So you only have a 2-element array, but that is harder, I think. Not so much harder, but conceptually, getting the big array to work first is easier. And then once you got that done, you say, well, I've got it done iteratively. Now let me see if I can make it even faster, even better, not faster, even better by cutting down the space requirement. So I don't need 100 elements anymore. I only need 2 elements, right? So you can go to that step too. So those are 3 steps in mastering Fibonacci and how it's done.
And that would be just better for the memory, right?
That would be for, you know, also code. The code is also simpler that way, because if you do it with a fixed array, your Fibonacci function is automatically bounded. It can't do anything more than 100, right? Because your array doesn't have space. But if you just do it with the 2 and keep replacing, like you said, you can keep going all the way to infinity, and providing your data type is big enough to hold the result. So that is the reason why this is better than just using a fixed size array. But in order to get the concept down, understand exactly what's going on, and visualize things, it's better to do it with the big array first, saying, all right, this will let me calculate all the way up to Fibonacci of 100, which you cannot do, right? Recursively, you cannot do beyond 45 even. Yeah. So with an array, you can go all the way up to 100. Although with 100, you'll see that you get inaccurate results. The results will be wrong. The results are wrong because the numbers are going to get big and they're not going to be fit in 4 bytes. So it'll roll over and you'll get wrong. However, you can use double. You can use double data type, and then you'll get the answers correctly all the way up to 100. Once you have that done, you can say, well, you know what? I'm not happy with just doing all the way up to 100. I want to go all the way up to infinity. Because in Python, for example, you can have numbers that go all the way, you know, endless. And so you can say, you know, I want to have something that keeps going on and on. So I'm not going to use an array. I'll just use 2 values, father, grandfather. That's all. Yeah. And that should do it. I think this is a good exercise. Okay. Good exercise. Ideally, get this done before Thursday. Okay. On Thursday, what we'll do is we'll take that and say, well, you know what, now this is how it works. And, you know, we know about return addresses and stacks, and now we'll start implementing a stack. Okay. We'll implement a stack and say, well, you know, this is a data structure the CPU could use to store return addresses, because the return addresses you put in will come out in the exact opposite order in which you put in, last in, first out. And we'll implement that in class and say, hey, that's how a stack is done. That is how recursion happens too. And in fact, you can use recursion, and you can use a stack in calculating Fibonacci too, although that'll be overkill and it's a waste again. So, but that's also possible. No, was this useful? We just did recursion, just one concept today mostly. Usually we try and cover a few different concepts. But was the coding a useful exercise, Hannah?
Yeah, it
Was it
really
like-
helps me with like, I don't know, being more mindful and stuff. I feel like
Yeah, exactly. That's the reason. Okay. Yeah.
I
when
a
you
lot of
code-
times just do things without thinking it and then check it when I run it. But
Absolutely, especially for kids in high school and all, like super duper important to, because in high school you're doing so many things and you're acting in a play and all, so there's so many things in your mind. and so it's hard to focus on a particular topic unless you're deep in it, and coding especially is good because it forces you in the deep end and say, well, you can't afford to think of Mamma Mia now, you got to think of the code, and you'll get it done. Yeah, thanks for that, and thanks for coding.
Yeah,
staying
I
on top
shared
of
it on Reddit, so it should be there.
Great, awesome. Thanks for that. And obviously ask any questions you guys have. Try and implement these alternative versions of Fibonacci, simple things. Share them on the Reddit and share them, and also say, I did it and these are my thoughts, and these are, and say one or two sentences about it too. And also Reddit posts and forum posts are super duper important for you, especially if you're planning to go on and major. You're going to go into colleges and grad school, you're going to apply and all. My 2C students from before are emailing me now. Apparently there's a deadline for applications to colleges, Georgia Tech and all, saying, hey, can you write me a recommendation? I stopped writing recommendations some years ago. I don't write recommendations, and because the profiles you are creating on Reddit so much more valuable than any recommendation you can get from any professor. So that is why it is important to start building up your profile right away, because you'll see right now you're asking questions about Fibonacci and things like that. By the time you are enrolled in my 2C and doing 2C quests, look at your own forum posts, look at your own forum. I know some of you are already enrolled in my 2C, I can see, right? And 2B, so you're in my 2B, but you'll see when you're doing 2C and you're making forum posts, go back and look at the forum posts you made in 2A in blue, and you can see you can see the difference. Okay, and it's not often that students get an opportunity to do that, because many times students do work and it's lost when they go on to the next year. Most of them it's lost. It'll be there. Testament to your persistence, patience, perseverance, and also your thinking and logical thinking, and your kindness in helping other people. All of those are like super duper valuable in your portfolio. So start building it up right now, and because you won't get a recommendation from me, even though you're top students. Every one of you is a top student, right? So I can't say this one is a topper, more top than everybody else. I can say that everybody is doing a great job. So I don't do these things, but these things that you create on your own, right? You don't need someone else. You don't need a professor, anyone, your mom or dad say, hey, please, this is a good story written by my daughter or son, right? No, because parents always say what you do is good. So you want to say, I've done. Nobody's telling you that this is good, but you take a look for yourself and they'll read it and say, well, I want that student in my college. Okay? So that is, you have an opportunity to do that. Start doing that right now. You have 2 more quarters to go to build up your entire portfolio. Look at some of the 2C students, okay? Especially the ones who've done my 2B and 2C, 2A, you can see the range of posts they've made, incredible ones, okay? Some of them are really profound. Some of them are better than excellent posts I've seen on Stack Overflow too. Is the insights they've got about the data structures, making professional quality posts. That will come to your rescue, right? When nothing else is able to help you, what you've created will come to help you, and then you'll be very happy. Oh, you're happy already, but that'll be super duper useful. Thank you all so much for your patience and sticking around again right past the end of class. I hope to see you all on Thursday. We'll actually implement a stack. Okay, we'll start talk about pointers and pointers, heap memory, and implement a stack, and then and then after we implement a stack, we'll talk about recursion again and say, hey, this is how it's being used. All right, thank you all very much. I'll see you on Thursday. Bye.
Thank you. Goodbye.
Bye, Simon.